Assalamualaikum and hi. We are from Group 9. We'll present about atomic force microscopy.
Assalamualaikum and hi, my name is Nashafika and I'm going to start with the introduction to atomic force microscopy. Atomic force microscopy is a powerful technique that enables the imaging of almost any type of surface, including polymer, ceramic, composites, glass, and biological samples. It is used to measure and localize many forces, including adhesion strength, magnetic force, and mechanical properties. It can operate in gas, ambient, and fluid environments. The ability of an AFM to achieve near the atomic level resolution on three essential components, which is cantilever with sharp tip, scanner that controls the XYZ position, and feedback control and loop. First, cantilever with a sharp tip. The stiffness of the cantilever to be less the effective spring constant holding atoms together, which is on the order of 1 to 10 nanometer. The tip should have radius of curvature less than 20 to 50 nanometer. The smaller it is, the better. And a curl angle between 10 to 20 degree. Second, feedback control. Force that exerted between the tip and the sample are measured by the amount of bending or deflection of cantilever. By calculating the difference signal in the photodiode quadrants, the amount of deflection can be correlated with height. Because the cantilever obeys Hooke's law for small displacement, the interaction force between the tip and sample can be determined. Lastly, the scanner. Movement of the tip or sample in XYZ directions is controlled by a piezoelectric tube scanner. For typical AFM scanner, the maximum range are 80 mm times 80 mm in the XYZ plane and 5 mm for the Z direction.
I am Farisha and I will proceed with the general components and their functions. First is probe tip, which senses surface properties and causes cantilever to deflect. The second one is cantilever, which the spring deflects as probe tip scans sample surface. Position sensitive photodetector, which measures deflection of cantilever. Feedback loop controls the sample position. Piezoelectric scanner, which positions sample XYZ with accuracy. And the last one is computer, which function is control system and performs data acquisition, displays, and analysis. So, how does AFM works? The first step is the AFM brings a probe in close proximity to the surface. The force is detected by the deflection of a spring, usually by the cantilever, and then the forces between the probe tip and the sample are sensed to control the distance between the tip and the sample. The cantilever is designed with a very low spring constant, which is easy to bend, so it is very sensitive to force. The laser is focused to reflect off the cantilever and onto the sensor. The position of the beam in the sensor measures the deflection of the cantilever and in turn, the force between the tip and the sample. There are different modes of operation, which the first one is contact mode. The force of interaction is strong. The non-contact mode, the force interaction is weak, and the last one is tapping mode, which the force of interaction also strong.
Application of atomic force microscopy in polymer science. AFM is very useful for studying the local surface molecular composition and mechanical properties of a broad range of polymer materials, including block copolymers, bulk polymers, thin film polymers, polymer composites, and polymer blends. It is capable of revealing surface structures with superior spatial resolution. Polymerid surfaces present inhomogeneities in microscopic scale, which can affect their properties of adhesion, wettability, abrasion, and degradation in the environment. Therefore, identification of inhomogeneities and its mapping have great importance in science and technology. Compared to other electron microscopes, AFM has been widely used for the study of polymers, as the cost of equipment maintenance is substantially lower. First, investigating morphology and structure. Polymer structures change at different scales of length. Features visible on larger scales include bars or fillers, and for blends of polymers, interfacial faces. Effects of processing like etching, heat or strain are also visible on the surface roughness or finish. AFM allows the structure to be visualized via nanoscale topography of the surface, typically taping mode. This mode yields image with excellent spatial resolution up to molecular and atomic structure. For example, Figure 1 shows the molecular and crystalline structure of rubrene. Rubrene is a polycyclic aromatic hydrocarbon used as an organic semiconductor in organic LED. The main color image with scan size of 5 micrometer shows single steps of the crystalline lattice. The inside black and white image reveals molecular level structure, highlighting the superb spatial resolution of AFM even in air. The small area in contact between the tip and the sample is responsible for the high resolution. This, in turn, is achieved by using ultra-sharp tip probes in addition to the taping mode, which results in very gentle sideways and vertical forces between the tip and the sample. Figure 2 shows a polyhydroxybutyrate covalent spherulite crystallization. Tapping mode face image of a PHP spherulite crystallizing at room temperature over a period of 3 minutes. The scan size is 1.5 micrometer and the scan rate of 440 Hz or approximately 10 seconds per frame allows clear visualization of the crystallization process. Smaller cantilever have higher resonance frequencies. They are also able to provide improved resolution and control for very small forces in the sub-piconewton range, which is extremely crucial when investigating polymers which are delicate and easily undergo deformation. Second, measuring forces and deformation. The cantilever used in AFM is one which is built with extreme force sensitivity, which makes it ideal for the measurement of a range of force magnitudes from piconewtons to micronewtons. There are two common ways to measure force. Single molecules are pulled to analyze the forces at molecular level, or polymeric materials are indented to evaluate their elastic and viscoelastic return following deformation. When the single molecule approach is used, one molecule is stretched between the tip of the AFM and the sample surface, and the deflection of the cantilever is measured. Once the spring constant and deflection sensitivity of the cantilever is known, a force versus distance plot is generated. These force curves provide information about intramolecular forces like the elasticity of the single chain or conformational transition, as well as intermolecular forces including interactions between polymer and solvent, and surface adhesion and desorption. These forces thus act inside or between the molecule. One case of force spectroscopy measurement is shown in Figure 3 using poly and lysine molecules during their desorption from a hydrophobic surface. The other method uses measurements of the deflection produced in the cantilever as the AFM tip indent in the sample. Conventionally used cantilever apply a force that is high enough to cause deformation in the polymers, which have modulus range from kilopascal to a few gigapascal. When a model is used to examine the indentation of the sample by the tip, data is generated on the elastic and viscoelastic characteristic of the sample at nanoscale.
So this is the advantage and disadvantage of atomic force microscopy. It is easy sample preparation and accurate high information. It can work in vacuum, air and liquid. Living system can be studied. However, it is limited vertical range, limited magnification range, data not independent of tip or sample can be damaged.
That's all from us. Thank you.